So let's talk about how ethers are made. If we have just a simple symmetrical ether, we can make that on a very large industrial scale by just doing an acid-catalyzed SN2 reaction of the alcohol that's related to it. So alcohol just has the one R group. The ether we want has those two R groups. So if we do something acid-catalyzed, the first thing that's going to happen is something gets protonated, usually. So we're going to protonate the O of the alcohol. That makes a good leaving group, right? We've essentially made a protonated hydroxyl group where the other alcohol molecule could come in and attack that carbon, which kicks out water. This has to be acid catalyzed, for instance, because OH itself is not a leaving group. But alcohol attacks, kicks out water. We now have over here is the entire new group that we've added. And then water just removes the H from the O that did the attacking, right? So protonate SN2, then deprotonate. That last step regenerates the acid catalyst, as we see happening so often in acid-catalyzed reactions. But this only happens with symmetrical ethers, because we just have to have a whole bunch of this alcohol with an acid catalyst, and it'll happen. You can separate it by distilling the lower boiling ether out of the way, right? There's no hydrogen bonding in the ether like there was in the alcohol. So ethers typically have a lower boiling point than their corresponding alcohols, even though it's almost twice as massive. Okay? Diethyl ethers boiling point is in the 30s, where ethanol boiling point is 70 or something like that. So ethers are excellent solvents that way, in that they're still polar, right? They have a dipole moment to them because of oxygen's bent geometry, but they're very low boiling, so it's easy to remove them by evaporation. So that's the industrial synthesis of something like diethyl ether, the solvent that gets used an awful lot. If we have a unsymmetrical ether, right, some sort of specialty ether that we need to make, the Williamson ether synthesis is the most common method. And it works great. It should not be a terrible surprise to us, because we've already talked a good amount about SN2 reactions, and that's all it is. It's just an SN2 reaction. I have an alcohol. I'll use a base like sodium hydride. Hydride is so good. H minus. That will attack the H of the OH. Those two electrons will go back onto the O, making an alkoxide ion, just like we did in the last chapter for deprotonating an alcohol. Now that alkoxide ion is an excellent nucleophile and can attack the partial positive, the electrophilic carbon of an alkyl halide. Okay? Alkyl halide really should be primary. An alkyl tosylate works just as well, if not better. CH3O TOS, right? That tosyl, that O tosyl group, that tosylate group is such an excellent leaving group. So same sort of thing can happen. Attack the carbon, leaving group is displaced. What I'm resulted with is a new OC bond, and then the C leaving group bond has broken away, and we're left with an ether in excellent yield, as long as the thing that we're attacking is primary. The reason for that, this is an SN2 reaction just like any other, where the nucleophile attacks simultaneous to the leaving group leaving. So this electrophile here has to be unhindered. It has to be wide open for attack by the nucleophile. If that were secondary or tertiary, the nucleophile would have a lot more trouble approaching that carbon from the opposite direction as from where the leaving group is leaving. So if we look at the Williamson reaction retrosynthetically, we have to look at it in that the primary side of the ether has to come from the one that had the leaving group. So let me draw this slightly more complicated ether here. Let's do a benzene ring. I like to put benzene rings in just for fun, right? There's a methyl group, and then O, and then just N-propyl group on the other side. So let's break this down retrosynthetically by asking ourselves which bond must be formed in order to make this compound. So if we look at the neighboring carbons, the carbons that are adjacent to the oxygen, I have a primary carbon right here because it has just one R group attached, and a secondary carbon right there. Right? So the primary side has to come from the alkyl halide. So what we're going to do is form through this retrosynthesis. We'll imagine breaking that bond right there, but the oxygen primary bond is the one that is formed. So the O side must be the O minus, the other side must be an alkyl halide, something like that. So in retrosynthesis, we're always looking at what was formed. So having a secondary alkoxide doesn't matter because it's the O that's attacking. What is important is that the alkyl halide is primary. If we tried to do it the other way around, for instance, if we did the alkyl iodide there and the N-propyl alkoxide, probably SN2 wouldn't happen quite as much. I mean, it might compete for it, but what's probably going to happen to a much greater extent, especially with this one, is E2. Take off that hydrogen, make the double bond, remove the leaving group, because especially on this one, if I do that, I have a double bond conjugated in with the benzene ring. So that's our E2 product. Undesired. That's why it's important to have a primary alkyl halide. Then elimination won't be competing. Okay, that's all. And like I said, anywhere we used a halide here, we could have just as easily used a tosylate. So if I had two alcohols, I could make one of them into a tosylate and the other one into the alkoxide. Right? And we can choose whichever one we want to make. Let's make a ether a little more complex way. If I run a Grignard reaction, right? Let's just do a simple Grignard reaction here with acetophenone, right? Methyl ketone attached to a benzene ring. Let's do an allyl Grignard, so double bond CH2 MgBr. Right, here's our C minus. Attacks the carbonyl to make an alkoxide. Just like we've done many times here. CH3, CH2, CH2, like that. Normally with the Grignard reaction, our second step would just be acidic workup to make that into an OH. But say we want to make an ether there. Instead, what I can do is add some sort of alkyl iodide. Right? Let's do ethyl iodide. That alkoxide essentially will do a Williamson ether synthesis. Right? Just a different way of getting to that alkoxide. So our product in this case would look like this. Oh, CH2, CH3, CH3, CH2. Like that. That's a good way of making an ether that has a tertiary carbon next to it, like that. So the retrosynthesis looks like this. We formed that bond last, and then through going back retrosynthetically, we could have made any of these bonds. starting with some sort of ketone. So depending on what it is you had to begin with, we could have either brought in this allyl group like we did here, or we could have brought in a methyl group if we would have already had this longer carbon chain there. So another little trick that we can do here is we can make a cyclic alkoxide. Take a look at this pretty neat reaction. Let's have an I at the end of a chain. Let's do 1, 2, 3, 4, 5 carbons. So 1, 2, 3, 4, 5. And then put an aldehyde at the end of that chain. All I want to do here is react this with methyl Grignard. Okay, attacks the carbonyl, makes an alkoxide. But now, if instead of reacting with acid, we just let it continue to react on its own, what will happen is this O- will attack the carbon next to the I inside of the molecule. It is an intramolecular Williamson ether synthesis reaction. Whenever something is intramolecular, we have a reaction that's happening inside of that molecule itself. So when we do something like this, it's helpful to look at what's going to be within the ring. So oxygen is going to be in the ring 1, 2, 3, 4, 5, 6. I'm going to make a 6-membered ring with oxygen inside of it. 1, 2, 3, 4, 5, 6. Carbon 2 has the CH3 attached from the Grignard reaction, and there's our product, a cyclic ether. So looking at this from retrosynthesis, the last step was just like that. So I had to have an O-, and I had to have a C with some leaving group attached to it, like that I. That O- in this case came from the Grignard reaction, where this methyl group came in and kicked up the O- on there. One other kind of interesting way of making a ether is with alkoxymercuration. We did oxymercuration back in the double bonds chapter first semester. That was where we did a Markovnikov hydration of an alkene, where an alkene like this got an OH on one carbon and an H on the other carbon to replace the double bond. So in this case, though, if we run this with the normal type of reagent, some sort of mercury acetate, this is trifluoroacetate, same sort of thing. But instead of in water, if we do it in some sort of alcohol, what happens is the first intermediate we get is that mercury ion. CH2. Right? We get something like that. And remember, in normal oxymercuration, we would have water attacking the more substituted carbon because that has a little bit more of a partial positive charge to it. But now, with this alcohol present, the O of the alcohol attacks that carbon, opens the ring, and with a proton transfer, we end up with this intermediate. I've got the OCH3 in the Markovnikov position. I've got that mercury there. And remember that second step, the sodium borohydride has H-, which will displace the mercury right there. Normal oxymercuration would just have an OH in the more substituted position. Alkoxymercuration done in an alcohol has an OR in that more substituted position, right? So just in very general terms here, if I have any kind of alcohol here, step 1, any kind of mercury salt, mercury 2+, and then ROH, step 2, sodium borohydride, what we'll end up with OR, just like that. So this is a way retrosynthetically of adding an OR group into a more substituted carbon that way. So if your retrosynthesis leads you to believe you have to start with something like this that had all the carbons in place and we need the OR on that more substituted carbon, an alkoxymercuration reaction would be smarter than a Williamson reaction.